We've all seen the images, right? The mushroom cloud. But what is a nuclear explosion, really? I mean, what's happening on a physics level in those first few critical moments? Well, that's what we're going to break down step by step.
So just try to imagine this for a second. In one single, silent instant, a light flashes into existence that is so brilliant it makes the sun look dim. This is the very first moment, the start of an event that unleashes the fundamental forces of the universe.
And in the few seconds that follow that flash, the physical world is just completely rewritten. But to really get a grip on its power, we have to look past the image and dig into the physics. So what is actually happening here?
Okay, first things first, we need to understand the anatomy of the event itself. Because a nuclear explosion isn't just a bigger, louder, conventional bomb. No, it's a completely different kind of physical process.
Now, this official definition here, it sounds pretty clinical, doesn't it? But let's unpack it. Very rapid release of a large amount of energy. We are talking about an unbelievable amount of energy, all unleashed in a tiny fraction of a second. It's so intense that it literally vaporizes the weapon and the air around it, turning it all into these hot, compressed gases.
And this is where that difference becomes crystal clear. On the left, a normal bomb. Its damage comes from the blast. But on the right, well, a nuclear weapon is playing in a whole different league. Yeah, you've got a blast, but it's thousands or even millions of times stronger. The temperatures are way beyond anything a chemical explosion can produce. And then there's the kicker, this invisible, penetrating radiation. So let's look at that first effect we talked about, the light and the heat. This is where the story of the explosion's impact really begins. It literally creates a temporary sun on Earth. Just take a look at that number, 7,700 degrees Celsius. To put that into perspective for you, the surface of our actual sun is only about 5,500 degrees, so this fireball is significantly hotter. This almost unimaginable heat is what drives that first devastating wave of destruction.
And here's the crucial thing. This heat doesn't just stay in one place. It radiates outward as thermal energy, and it does it at the speed of light. That means it arrives almost instantly, causing horrific burns and starting fires miles and miles away. And look at that last bullet point. This isn't just some side effect. That heat, that thermal energy accounts for a massive chunk, 35 to 45%, of the weapon's total power.
All right, let's move on to the second major effect, which comes right after that flash of light and heat. This is the main cause of all that physical destruction you see in the photos, the blast wave.
This image from the source material explains it perfectly. This is not just wind. See that sharp, almost vertical line on the graph? That's the shock front. It is a literal wall of compressed air that's moving outward faster than the speed of sound. It's a sudden, violent, crushing jump in air pressure.
And this quote from the source really nails the difference. You know, a normal explosion might blow a hole in a building, but a nuclear blast wave is so huge and lasts so long that it can completely surround and crush an entire building. It doesn't just damage a part of it, it causes total, catastrophic failure.
And this, well, this isn't theoretical. This is what that pressure wave actually does. When you look at the absolute devastation at Hiroshima, the main reason for this flattened landscape was that immense, crushing force of the shockwave we just saw on the graph.
But the destruction doesn't end with the heat and the blast. Oh no, there is a third, totally invisible component that makes these weapons unique. A danger that sticks around long after that fireball has faded away.
So we've seen the effects of heat that can be felt for miles and a blast wave that can level cities. But what about the dangers you can't see or hear or feel at all?
It turns out there are two distinct waves of radiation. First, you've got the initial radiation. This is an intense, immediate blast of penetrating rays and particles that are all released in the first minute. But then you have the residual radiation, what we all know as fallout. This is the radioactive gunk from the bomb itself that gets blasted up into the atmosphere and then slowly falls back to Earth, contaminating everything for days, years, or even longer.
And this table, well, it lays out the biological cost in a really sobering way. Let's just walk through it. At a relatively low dose, maybe 100 to 200 rems, symptoms show up in a few hours, but therapy works. But as that dose climbs, look at how fast the symptoms appear. It goes from hours to just minutes, and the damage shifts from your blood-forming systems to your gut. At the highest doses, over 5,000 rems, it attacks the central nervous system almost immediately and is just lethal. That is the direct, cellular-level damage from that invisible radiation.
So here's the ultimate takeaway.
The terrifying destructive power of a nuclear weapon doesn't come from any one thing. It's the catastrophic combination of all of them, all hitting at once. An intense flash of light, a wave of scorching heat, a crushing blast wave, and a flood of invisible, cell-destroying radiation.
You know, understanding the physics behind all this is one thing. It shows us what's possible. But it also serves as this really profound reminder that while science can unlock the power of the atom, the ultimate responsibility for how that power is used or not used, that always rests with us.